So already I explained some of the examples of an open loop control. So washing machine is an example for an open loop control system. So in washing machine, we are setting the time period. So whether your washing machine is an automatic washing machine or semi-automatic washing machine, what we are doing is we are setting the time period. So since the time period is set, irrespective of the quality of the output, your system will come to a halt once the time period is over. So an operator must stand to inspect the cloth, whether it is as per requirement. So if it is not properly washed, you have to again operate the system, or you have to again control the system. So that means quality will not be as per requirement in open loop system because it is time based. And if I want to make it a closed loop, what I require is, I require sensors, sensor which will sense the quality of the cloth. And what is the required quality? I can feed it to a computer. And this required quality is being compared with the sensed quality. And if there is a difference, I can, using that signal, I can have a time controlled, or it can be controlled by a computer. So if a computer controls the operation of your washing machine by setting a sensor, that is called closed loop way of controlling. So it is very expensive. Your systems becomes very complex. People cannot afford to buy such a washing machine. So that is why washing machines are made under open loop, because they are very simple. A normal people can handle it. Only requirement is we require an experienced user or experienced operator. Then the quality the operator can control, because operator can set the time period according to the quality of the cloth. That means if you want a better quality control under open loop, we require experienced personnel for that. The cost of the system will be reduced. The complexity of the system will be reduced in open loop systems. But not all closed loop systems are very complex, because we know some of the day-to-day applications where closed loop systems are employed with the minimum cost. One is the heat control of a room, the air conditioning, the heat controller, or the air conditioning system control, or room heating mechanism. These are simple procedures where we can easily control the temperature, humidity, etc. of a room by a simple procedure. The cost is not that very high. So not all closed loop systems are complex and expensive. Some closed loop systems are very cheap. So I can design such systems if they are very cheap. Then another example of an open loop system is a traffic control mechanism. So how we are going to set a traffic control? First of all, we have to study the traffic flow at a particular junction for quite few number of days. So some people will stand in the traffic junction and they will study the traffic flow for few days. Then they will have the control action. They will set the time period according to their studies, based upon their studies. But if the traffic flow is different from what they have studied, then there is going to be error in the system, or your efficiency of your system will be very poor. So an open loop system regularly needs what is called a recalibration. That is, you cannot depend on the studies for a long period. That means you have to recalibrate the system once in a while. Again you have to study the system, and again you have to set a new time period according to the flow of traffic. That means all open loop systems require calibration or recalibration so that I can have a better quality output. Because in traffic control we know that during Sundays, when there is no traffic flow, still we have to wait at the junction for a long period. So it is quite inefficient. We are wasting the fuel. So if you want to make it a closed loop mechanisms, I require sensors. So sensors can be put at the junction. And this sensor will take the pictures of the traffic flow. And this information can be sent to a central computer. And the computer can control the time period of operation. Then it becomes a closed loop mechanism. Your output will be as per requirement, or it will be highly efficient. But the problem is, you have to have cameras installed at the junction as a sensor. So these cameras will take the picture of the traffic flow, and camera will send the information to a computer, and the computer controls the time period, so it becomes a closed loop. But it becomes highly complicated. It becomes very expensive. That means every practical applications, we cannot go for closed loop mechanism, because some closed loop mechanisms are very complex, they are very expensive, and people cannot afford to buy such products. So everything depends upon the cost of the product. So if cost is an important factor, then we use open loop systems. And if cost is not that important, then we can use closed loop control. So that is the difference between open loop and closed loop controls. So open loop control, you have to have a definite relationship between output and input. That means I require. So in control engineering, what we are going to control, we call it as a system, or we call it as a plant. So we have a plant to control. For example, DC motor, that is a plant, or that is a system. So this plant will have an input signal, and it is going to have an output signal. So this output is not fed back if it is open loop. So in open loop system, if the plant is properly designed, if the system is properly designed, and if I know the relationship between output and input, and if there are no disturbances, if there are no parameter variations, and if I can do the calibrations, recalibrations, then I can design it under open loop. So open loop systems, we require accurate plant design. That means the components which are used for designing the plant, for designing the system, they are very expensive. That is open loop system, your plant is expensive. Whereas if it is closed loop, even if there are disturbances internally or externally, even if there is a calibration problem, still I can correct I can control my output by feeding back a certain portion of the output and fed it back to the input. So that is called a closed loop control. So in closed loop control, your plant design is not very important. Disturbances in the system, it is not important. External disturbance or internal parameter, it is not going to have any effect on the system, because we have a feedback, and this feedback can correct the disturbances either internally generated or externally generated, and I can easily control the output of the plant to our requirement. I can make the output error free. So what is meant by error? We call it a steady state error. And we have a transient error or transient performance. So every system, when I apply a certain input, there are two types of output. One is called steady state output, and another is called transient behavior or transient output. So this transient in a system is because of the presence of energy storage elements. All engineering systems will have one or more energy storage elements present. You cannot have an electrical control, or you cannot have an electronic system without inductor, without capacitor, etc. You cannot have a mechanical system without mass, without spring, etc. That means every engineering product will have presence of energy storage elements. So these energy storage elements will have a stored energy. So during the switching action, when I apply a signal and when I close a switch or when I open a switch, what happens is there is a transient period. During that period, your output can be exponentially varying or So this type of variation, exponential variation, that is what is called transient. So after a certain time period, these transient will settle or transient will disappear and we will get an output which is a function of input. So that is what is called a steady state. That means from a plant, what I am expecting is an output corresponding to my input. So that is what is called a steady state. So this steady state performance of a control system, we can control it by controlling the poles. So I can have more poles introduced in a system to have less steady state error. So here what I meant by steady state error is, let us say that I have a lift. So I entered the lift and operated the switch. For example, I want to go to a third floor. So when the lift starts moving, what we expect is no vibration, no oscillations. So these oscillations or these vibrations are what is called transient behavior. So when I design a control system, for example, when I am designing a passenger vehicle, passenger car or passenger train, when a train is started or when a train is stopped, I don't expect any vibration or I don't expect any oscillations. Accordingly, I must design it. So this operation, this type of operation, we call it a transient, an exponential variation or oscillatory motion. So we don't want such operation in passenger systems. So that means a lift, when I press the button, it should move smoothly without any oscillation, without any vibration. And it should move as fast as possible and it should land at the required floor level. So if I press the third floor button, the lift should travel very smoothly without causing any discomfort to the traveler or to the passenger, and it should come to the third floor level. And when it stops at the third floor level, your level difference between your lift floor and the level of the floor should be in the same level. So there should be zero difference between the lift level and the floor level. If there is a difference in the floor level and the lift level, we say that there is a steady state error. So this steady state error may cause accidents. That means when I am designing a lift, what I require is smooth movement, and when it stops, I require zero error, zero steady state error. The floor level and the lift level should be at the same point, no level difference, so that there will be no accident in the system. If there is a level difference, if there are people inside the lift where they have, some are blind people, then there can be accidents. Such accidents do take place in practical systems if systems are not properly designed or systems are not properly maintained. So all engineering systems, we take proper care in designing and making it, but we have to maintain it properly. All control system, we have to maintain it properly. So maintenance is another requirement of all system control. So proper designing, proper analysis, proper designing and proper maintenance. These are very important when you are using an engineering product. So we have transient control and we have steady state control. So how we are going to control or your steady state accuracy is by controlling the pole locations, or we say that by controlling the type number of a control system. So we are going to learn what is called type 0 control, type 1 control, type 2 control, etc. So these type numbers like type 0, type 1, type 2, etc. can control the steady state behavior of the system. As the type number increases, your steady state performance becomes better and better. This is what we are going to learn in control engineering. And this type number is a function of number of integrators present in the feed forward path. So we will learn what is meant by feed forward path, feedback path, etc. So while designing a control system, I have to have transient performance properly set and steady state behavior properly controlled, then I must ensure that your system is stable. So these are the two parts of control system study. So first part of your control system, I am going to learn about what is meant by transfer function. So how you are going to derive transfer functions of various control system components. So various control system components are amplifier, potentiometers, synchro generator, synchro transmitter, tacho generators. So these are some of the control system components. Then you will have motors. We call it as, in control system we call it as servo motors, DC servo motor, AC servo motor, etc. So servo motors are motors employed for servo mechanisms applications. Already I mentioned about servo mechanisms. In servo mechanisms, your output is a mechanical position, a velocity variation or acceleration. Driving a car, so that is an example of a servo mechanisms. Driving a scooter, driving an, these are where we are called, it is called servo mechanisms. So in servo control applications, we require different types of motors. We call it as DC servo motors, AC servo motors, etc. And we should know how to mathematically model those servo motors. Then how to model an amplifier, how to get the transfer function of a potentiometer, the transfer function of a tacho generator, then transfer function of different types of control elements. This is the first topic we are going to learn in control engineering, that is transfer function derivations. So once you mathematically describe a system by a mathematical model, then I can arrange these models in a certain fashion. I call it as a block diagram. So normally a control system will have many blocks. There will be many forward paths. There will be many feedback paths. So that means your block diagram will be complicated. So such a block diagram, if we can convert into a single block, we call it as overall transfer function of the system. I can make use of that overall transfer function for further studies, for further analysis. So that means your complex block diagram, I must convert into a simpler block diagram. So I can use two procedures. One is block diagram reduction technique. So using this block diagram reduction technique, I can convert a complex block into a simpler block. And once I have a single block like GS, that is a transfer function, I can use it for analysis and design. Then if your block diagram is highly complicated, very complex, block diagram reduction will be very time consuming procedure. In that case, I can go for a simpler method, that is what is called a signal flow graph. Using signal flow graph and what you call it as Mason's gain formula. Signal flow graph and Mason's gain formula, I can convert a complex system into a simple model with less effort. So that means you should know block diagram reduction technique and signal flow graph and Mason's gain formula. Our Mason's gain formula is going to be employed for finding the overall transfer function of the system. And once you have the transfer function, we are going to define different types of transfer function. What is the transfer function of the feed forward path? Transfer function of the feedback path? What is an open loop transfer function? What is the closed loop transfer function? And once I have this open loop transfer function, we call it as GSHS. So this GSHS, this function is very critical in control system analysis. Then I have 1 plus GSHS is equal to 0. This is what we call a characteristic equation. Characteristic equation. So 1 plus GSHS equal to 0. This characteristic equation is going to be employed for finding the absolute stability using Root stability criterion, or some people call it the Root stability criterion. So, Root stability criterion, I require 1 plus GSHS equal to 0. And 1 plus GSHS is equal to 0, we call it as characteristic equation. Then I can make use of GSHS, that is the open loop transfer function, for sketching the Bode plot. So, the magnitude plot and the phase plot can be constructed by using GSHS. And using this Bode plot, I can find out what is the gain margin and phase margin, whether it is stable or not, how much is stable or how much unstable it is. So, this information can be obtained from Bode plots. Then I can design a corrective mechanisms, or I can have a compensation mechanisms. Then a second method for analysis is what is called a root locus. So, I can find out the various poles and zeros of an open loop transfer function GSHS, and using this open loop transfer function, I can find out the closed loop behavior using a root locus. What is meant by root locus is locus of the roots of the characteristic equation. As the value of k is varied, k means your open loop gain, value of k is varied or value of zeta is varied. Zeta means damping factor or damping coefficient. So, as the value of k changes, your locations of poles and zeros will change. As the value of zeta changes, your pole zero locations will change. So, I can find out the locus of the roots of the characteristic equation using GHSS function, and that is what we call root locus. And this root locus, I can use it for finding the what is called closed loop behavior. So, if there are locus in the right half, if there is a certain part of the root locus is present in the right half, immediately I can say that that is unstable. That means there should not be any locus present in the right half of the S-plane. And if there are locus in the right half, I can pull the root locus towards the left by providing compensations or by providing pole zero control. So, root locus, whether how you are going to pull it towards the left in order to make it stable, so that we will see in root locus technique. Upon root locus technique, we are going to plot the root locus of a system for various values of k and various values of zeta, and we can determine the gain margin and phase margin. Then in third method, that is what we call a polar plot or Nyquist plot, where I can use GSHS of a minimum phase system or GSHS of a non-minimum phase system. I can plot what is called polar plot. And using that polar plot, I can find out the gain margin and phase margin. So, this is what we are going to learn in conventional control theory or classical control theory. Then we will have a chapter on state space analysis. So, that is a time domain approach. And the advantage of such an approach is I can use it for any type of control. Need not be linear. So, I can use it for linear or non-linear, time invariant or time varying. What is called a single input, single output, or multiple input, multiple output. That means any type of control I can use that modern control method, that is state space analysis. So, this is what I am going to teach you under control systems.